So let's take a look at this idea of torque and lever length and how they relate. Now what we're going to talk about here is a balanced system, okay? So what we have to do is we're either going to have to change the load or the resistance based upon the length of the levers because again, we want to achieve a balanced lever system. This goes all the way back to that formula that the force times the force arm length is equivalent to the resistance times the resistance arm length. Another formula to keep in mind is that of mechanical advantage. Remember that mechanical advantage is the effort arm over the resistance arm. And so here, first we need to do is define what class of lever system this is. Got it? If you said this is a first class lever system, you're correct. It's defined as first class because the fulcrum lies between the two arms. Now, if the force arm and the resistance arm are equivalent, say 15 meters, according to our formula, the force and the load must be equivalent in order to balance the system. This also provides a mechanical advantage of 1 and balances the lever system. What class of lever system is this? Aha! It is also a first-class lever system because once more, the fulcrum is in between the two arms. Now, when we're looking at this, notice things have changed in order to balance the system. We can now lift a much heavier weight with much less resistance. The reason that is because the force arm becomes much longer and it requires less force in order to move a larger resistance. This is sort of like sticking that stick under a heavy rock in order to get it to move. The mechanical advantage here is greater than 1 because that effort arm is much longer than the resistance arm. Effort arm over resistance arm. This again is still a first class lever system because of the position of the fulcrum. However, as the force arm gets shorter and shorter, the fulcrum moves down this end, we need a much larger force for a relatively smaller resistance. But now, if we apply the force here, we can see that this end of the teeter-totter or the balance system has a much larger range of motion as we would push through it. So, again, here we're sacrificing applying a lot more force in order to gain speed and range of motion at this distal end. Here, the mechanical advantage is less than 1 because the effort arm is much smaller than the resistance arm. What type of system is this? This is a second-class lever system because the force arm is longer than the effort arm, and they are both on one side of the fulcrum. Therefore, in this system, the mechanical advantage is always greater than 1. Now, if we place that weight halfway between the fulcrum and the effort, it requires half of the force in order to lift it in order to balance the system. That's important to note. As that resistance moves closer to the axis, it increases the mechanical advantage, meaning we apply the same load and we get more work done, but it decreases the range of motion that we can move the resistance. Let's move that resistance all to the other side. The closer the resistance is to the force, the less mechanical advantage, but the greater the range of motion. Again, in this system, the mechanical advantage is always greater than 1. But the closer that resistance is to our force, the closer the mechanical advantage is being to 1 exactly.